All right, YouTube, Professor Tomney here. It's time for another lecture. This is going to be a part video lecture on my part where I'm actually going to be speaking and showing you things on the screen. And then you're also going to see the actual screen portion that's up here that I can write on and I can utilize. So there may be some switching back and forth as I do that. The first thing that I wanted, so the subject, what are we talking about, right? Before I sort of dive off on this here. We're talking about Newman projections today. So Newman projections are ways that we can view molecules that are a little bit different than what we're used to so far. So how do we normally consider a molecule? Well, when we draw the molecule, right, the molecule tends to take on one of several forms. So if I'm doing a condensed molecule, I may have something like this, and we're just going to start with ethane. It's a very simple example when we're doing Newman projections. And I should mention Newman projections, because of the complexity, is they're probably going to be broken down into multiple lectures. So it certainly will not just be one. So here's ethane, right? We could also draw this as a sort of a line diagram. Now, typically we don't represent it like this as just these two dots, right? If we're going to do line diagrams, we usually have multiple ones like this. However, this technically is representing ethane as well. But every time we look at this, or every time we consider this, and you may want to consider kind of the three-dimensionality to it that we could also have, right? Where we have wedges and dashes. So some of this is in front of the carbon, some of it's behind the carbon, some of it's within the plane of the carbon, and then we could also consider the opposing carbon also having something like this, where we would have hydrogens on all of them, right? And that would be ethane. I have a CH3 on one side, I have a CH3 on the other side. Okay, so when I draw molecules like this, when you see them in class like this, when your professor puts them on the board, what you're really looking at, okay, let me get my model here. What you're really looking at, this is a molecular representation of ethane. You're looking at it from the side like this, right? So here's the portion when we're talking about what's in front, what's in back of you, and then what's in the plane of what you're actually looking at right here. And then same thing when we're up here, right? One of these is in the back, one of these is in the front, and the one that I'm holding down here could be considered to be in the plane of the board that would match that structure that we just drew. So you're really, when you're drawing them out most of the time, you're looking at them from this sort of perspective that we have right here. I would strongly encourage anybody, even if you're following along with the YouTube videos, but especially when you're in your lecture class, whether you have me or somebody else, you want model kits. Model kits are absolutely essential when you start getting into the subjects of stereochemistry and conformers, different conformations of molecules. Okay? So what a Newman projection does is it's going to take a molecule and turn it on its side. So we're going to start looking at it this way, okay, like this, instead of this way. We're going to be looking just like this. So what we're really doing is we're taking two carbons and we're going to, it's called sighting, okay? You'll hear people talk about sighting down a certain carbon bond. And when you sight down a carbon bond, you're taking what you would normally have on the side and you're looking at it face on, just like this. All right, so before we get too far into that with the model, let's take a look at how we would draw a Newman projection, a representation of a Newman projection. So bringing the whiteboard back up. If I clear this off, the easiest way to draw a Newman projection is to start, and I'm by no means an artist, but I do have some practice doing this. You're going to start by drawing a circle as best you can. Okay. And then right over top of that circle, you're going to do kind of like a peace sign with a little dot in the middle. So you can call this an upside down Y or something like that. Note that you want the edges to stick out past the circle here. Okay. And then the other thing we're going to do, attached to the circle, we are going to do sort of an upside right Y, or a proper Y, instead of upside down. Just like this, with those stems that are kind of coming off of that carbon, right? So what do I really have here? Well, when I'm looking at this portion right here, when you have this, okay, this is equal to the carbon in front. So the front carbon that you're looking at, specifically this circle right here is the carbon, and these 3 points are going to be the substituents that are found on that carbon. Okay, and then that carbon, it doesn't just have 3 bonds, it has 4 bonds. And the 4th bond that that carbon has is to the other carbon that's in back of it. And so we can draw this separately, and this portion right here is going to be equal to the carbon in back, right? And so when you mix these two together, you get the Newman projection. You're really looking at 2 carbons, one in the front, one in the back, and then you're looking at the different substituents and the positions they have to one another. Now, I mentioned at first that ethane is one of the simplest examples. So you at least need 2 carbons in order to do this, right? Because when you're doing this, right, the front carbon is a CH3. So there are 3 hydrogens present on the front carbon. And the back carbon is also a CH3. So there are 3 hydrogens on the back carbon. So what does that look like? Well, let's bring the screen back up with the model kit. Okay, the front carbon is going to look like an upside down Y. The back carbon will look like a proper Y, but there will be hydrogens at each point here. So keep this structure in mind, okay, as we are taking a look at this. So here's the model kit. All right. Looking at this from the front, get my hand out of the way here. Here's the front carbon, right? And so what you can see is this front carbon, the little black carbon right here, is acting or appears to be an upside down Y. So here's the top point, right? And then these 2 bottom points are the bottom part of the Y that are sort of jutting out beneath that carbon. And I'm going to hold it this way for a second so you can see that, right? So that's your front carbon. Now, if you take a look right back here, I also have a back carbon. The back carbon right here has a set of 2 hydrogens up top and 1 below that's right here. And so that's the proper Y that's facing upwards. And so if I were to turn this, you could see that right there. Okay, and that's an example of a Newman projection. Very simple one. And what's important to understand when you're starting to look at Newman projections is that single bonds or sigma bonds have free rotation. So when I have something like this, right, I have the ability to rotate this bond, and it can continue to rotate around and around. So these can move as well as the back portion. And so what's really happening is the molecule can move back and forth like this constantly between its single bond, and that means that these are always passing one another. Okay? So when we start drawing Newman projections, there's going to be 2 major types of Newman projections, and then there's a couple of sort of subclassings that we're going to talk about in the next lecture. So we've already seen one of them, which we drew. The first one looked like this. We have right here, right? So this example that I'm showing you right here, I kind of put it flat like that. This example right here of this Newman projection, it's called a staggered Newman projection because these groups are staggered from one another. Okay? Now, what can happen is that as this bond has free rotation and these move, they can come into alignment with one another, how they just did here. So now look at what happens when I turn this towards you. Now, right, you can't really see the difference. So before you could see the Y portion that was coming out of the back. Now if I hold this up properly, and it's a little bit difficult with the camera here, but you should be able to see these are very similar in terms of overlapping. These bonds right here, if I turn this way, right, these 2 bonds are aligned with one another. They're overlapped. These two bonds are aligned with one another and overlapped. And finally, these two bonds, right? So if I put it this way, you can see how they're completely aligned, perfectly aligned with one another. And so that's another form of a Newman projection that we can have. And that form of the Newman projection is referred to as an eclipsed Newman projection. Okay? So over here, we have the staggered version of the Newman projection. And then we can also have an eclipsed version. So for the eclipsed version, technically these would be completely overlapped with one another. For the sake and the purpose of drawing these or showing them in a class, you want to still give some small amount of space to basically show both atoms that are close to one another, right? So something like this. This would be an example of the eclipsed Newman projection. So when we're working with these, okay, it's important to keep in mind that one of these is going to be high stability and low energy, and one of them is going to be low stability, high energy. So when I'm looking at this, the staggered should appear to be the one that is going to have greater stability. So this is going to have high stability. We'll talk about why in a second. High stability. And remember that these are inversely proportional, right? So if something is low, in the example I always like to use is a hyper child. If the child has a lot of energy, right, you gave them a lot of sugar, that's not a stable situation. So these are inversely proportional. You have high stability, that means something is low energy. Okay? If you have something that is low stability from a chemical standpoint, then you're going to have something that's relatively high energy in comparison. Okay? So let's think about why the eclipse is going to be higher in energy. There's really two reasons, okay? And these two reasons, I'm going to clear this off here and we'll take a closer look at the eclipsed so that we can understand what's going on. Right, so these hydrogens are basically, they're starting to overlap and get very close to one another. So there's two considerations that we want to talk about here. And there's strain that is being introduced to the molecule. So the first type of strain that we're going to talk about is torsional strain. And when we deal with torsional strain is due to bonds. That eclipse. All right, so in other words, if you were to take a look at this, look at this right here. These bonds right here are eclipsing one another, meaning they're passing right in front of each other, okay? Compared to if it was staggered, so let me set this back up in a staggered position, these bonds are no longer overlapped, right? This one has some open space out in front, whereas these also have some space. In comparison to if I align them, there is a perfect alignment, or these two are eclipsed with one another now. This bond lines up with this bond, right? So what's the problem with that? Well, the problem is bonds are made up of electrons, and electrons have repulsive forces, right? They're negatively charged, so they're going to try to repel one another. So it's not ideal to take these bonds and align them, electrically speaking, right over top of one another. That creates torsional strain. Okay, so torsional strain is when the bonds basically, they're coming closer, and then they eclipse, right? So the bonds are right over top of one another. And in this case, the molecule will most definitely attempt to rotate back into a staggered position. Again, it has free rotation, so it can be moving all the time. But if you were to average all that out, it's going to attempt to stay in a staggered position more often than an eclipsed position from a stability standpoint. Okay, so let's go back and take a look at the other thing we want to consider. The second one, and you'll hear about torsional strain throughout organic chemistry a little bit, but this second one is going to become very important, okay? And that is steric strain. And you will hear us talk about sterics over and over and over again in organic chemistry. Sterics will not go away. So steric strain is when you have larger atoms, so large atom groups, and it can be any type of atom. Even hydrogens have slight steric strain. So this isn't the best example to look at steric strain, but you can get the general idea, okay? So it's when you're going to have larger atoms that are going to conflict with one another in terms of their spatial arrangement. So think about an atom, right? If I have some atom X, and X is bonded to, some carbon, atom X still has its own orbital and its own electrons. This is an oversimplified version, right? But there's electrons surrounding atom X. So if I keep another atom X in very close proximity, or an atom Y, or whatever this atom might be, right? Meaning if they're eclipsed like this, and then this atom also has electrons sitting around, when you look at these two coming close together, the electron clouds, you could say, or the valence electrons in the outermost shell, are going to start conflicting with one another. They're going to start having this strain, and this is referred to as steric strain, when these larger molecules start getting in the way of one another and having these issues. Okay, so it's not horribly prevalent here because I've only got hydrogens. So these two hydrogens are fairly small and can give one another some space still. But as soon as I upgrade even to something like methyl groups, which we'll take a look at in the next video, you're going to start having serious issues, right? So just imagine if instead of hydrogens, these were atoms that were close to the size of my fist, right? So now, when these two come close to one another, they're conflicting with each other. And there's going to be a lot of electronic clash going on there. That's referred to as steric clash. Sterics in general, in organic chemistry, sterics refers to large groups or crowding around a specific area on an organic molecule. And sterics is not a good thing. You don't want to have a lot of sterics. You'll often hear it in negative terms. Steric strain, steric hindrance, things of that nature. Okay, so we're already at 18 minutes. I'm going to cut off the lecture here because we do have more material that we're going to cover in the subsequent lecture. So thank you guys very much for joining me for this. Hopefully you can get a hold of a model kit to work with. You definitely want something like that while you're doing Newman projections and several of the other lectures we're going to be coming across here. So please remember to like, comment, and subscribe. That's how you'll get all the up-to-date information. I'm happy to answer any comments if you have questions. And thanks a lot for stopping by and taking the time to learn with me. So I will see you guys for the next lesson. Take care.